As we gaze into the vastness of space, we also peer back through time, discovering that the distant wonders we observe mirror the ancient phenomena that once thrived in this corner of the universe. The breathtaking scenery, billions of light years away, is, in essence, the same as the stunning landscapes we experienced here billions of years ago. If we had a time machine capable of taking us back into the past, we wouldn't rely as heavily on massive telescopes that push the boundaries of the observable universe. This discussion sparks an intriguing idea. Everything mirrors each other across the globe. So why not focus on one specific area, dive deep into its history, and set aside the rest of the world? The story of this one region mirrors the story of what unfolds all around us. Yet this argument does come with a noticeable downside. Various regions, whether close by or distant, play a role in shaping any selected sample area. So how can we overlook their influence? Light travels incredible distances and plays a crucial role in shaping events in the sample region. Focusing solely on one area, while disregarding others, means we must acknowledge their impact in some capacity. The factors from far away that impact the sample area are, on average, similar to those that were present in the sample area a long time ago. Can we come up with a way to swap out distant elements with those from the sample area from a long time ago? Cosmologists have a unique challenge. Unlike many other scientists who can engage in hands-on experimentation, they must hone their skills in conducting imaginative experiments and focusing on specific areas of the universe. Creating something that influences itself is pretty straightforward. Here's the secret sauce. Imagine our corner of the universe, or any other selected area, being enclosed by imaginary reflective walls. The chosen location is wrapped up in a cosmic container. Light rays bouncing around inside the box are reflected back and forth by the walls, creating a captivating dance of illumination that never escapes. The ancient light from nearby objects now shapes the contents of the box. And generally, this light mirrors what we typically get from far-off sources. We've successfully isolated a sample region where its current state is shaped by its historical conditions, and these conditions match those found in other locations. The hypothetical reflecting walls of the cosmic box need to be flawless in every way. They should transmit nothing, absorb nothing, and reflect everything, including light, gravitational waves, particles, neutrinos, and anything else that travels through the universe. A divided universe sheds considerable light on our understanding of this topic. Picture this. Imaginary partitions, comoving and perfectly reflecting, slice the universe into a multitude of distinct cells. Every cell holds a prime example, and is spacious enough to encompass galaxies and clusters of galaxies. Every cell surpasses the vast scale of irregularity found in the universe, and the contents within all cells exist in identical states. A partitioned universe operates just like a universe that has no partitions at all. We take it for granted that the partitions are massless, meaning their insertion won't change the dynamic behavior of the universe. All cells maintain similar conditions, reflecting the same state as when partitions were absent. Light rays that typically originate from far-off galaxies stem from local galaxies of the past, journeying through vast distances via multiple reflections. Generally, the outflow from a region mirrors and reproduces what comes in, often directed towards another area. Through these engaging, detailed balancing discussions, we uncover that partitions do not influence the behavior of the universe. We've demonstrated that shifting and reflecting partitions don't alter the essence of the universe. Now let's take down all the partitions and keep only the walls that surround a single cell. What unfolds within this cell, or cosmic box, mirrors exactly what occurs in every corner of the universe outside. Both those within and those outside the cosmic box see essentially the same view. An observer within the cosmic box boldly proclaims to Witom, "I reign supreme over infinite space." In his bad dreams, he navigates a looking-glass universe crafted by a cosmic jester. The walls of our cosmic box are stretching apart, and this happens at a speed defined by the velocity-distance law. When considering a cube-shaped box with sides of length L, it's important to note that this length L is directly proportional to the scaling factor R, which remains consistent across the entire space. Opposite walls are moving apart at a relative velocity of HL, with the Hubble term defined as HdR equals RdT. Imagine if L is 100 megaparsecs, then this relative velocity reaches an impressive 10,000 h kilometers per second, given a Hubble term h of 100 h kilometers per second per megaparsec. Irregularities can be distracting and don't add much to our conversation at the moment. To keep things straightforward, let's set aside any irregularities and picture the universe as perfectly smooth. Irregularities can be revisited later if they prove to be significant. In a perfect universe, the cosmic box can be as tiny as we want, and everything inside will still reflect the bigger picture. When L is just 1 kiloparsec, the walls are moving apart at a relative speed of 100 h meters per second. At 1 parsec, that relative velocity drops to 10 h centimeters per second. When L is 1 meter, the velocity is about 1 h centimeter per million years, and the trend continues from there. The speed of the moving walls can be adjusted to be as minimal as we desire. Of course, the box should always be larger than the size of the items being examined. When we dive into the fascinating world of radiation, our box must be spacious enough to hold the longest wavelengths we are curious about. A star, naturally, can't be confined to a box with just 1 cubic centimeter or even 1 cubic kilometer of space. Yet we can transform matter in small boxes to shine brightly, reminiscent of the unrefined universe. When the smoothing process exceeds our comfort level, L can be adjusted to a sufficiently large value to include the elements that capture our interest. The key takeaway here is that L needs to be significantly smaller than the Hubble length LH, which is about 10 billion light-years. Let's dive into some of the exciting advantages of the cosmic box now, with even more surprises waiting to be uncovered later on. Within a compact space, we have the liberty to explore the wonders of Euclidean geometry. We can bend space using either spherical or hyperbolic geometry, but in any small area, it still feels almost flat and Euclidean. Studying cosmic phenomena in a controlled environment is a significant benefit, as it allows us to focus without the complexities of large-scale space curvature. Anything that can be clearly explained within the limits of a cosmic box stands apart from the broader structure of space itself. This will uncover how the answer to the intriguing mystery of the night sky, known as Olber's paradox, is independent of whether the universe is open or closed. This insight reveals why the cosmic box serves as a key tool in unraveling this riddle. Since box L is relatively small in comparison to the Hubble distance LH, the walls are moving away at a velocity that is minuscule when set against the speed of light. Within the box, there's no requirement to differentiate between Doppler and expansion redshifts. Light dances back and forth, and as the walls gradually drift apart, the cumulative effect of countless tiny physo-Doppler shifts mirrors the redshift caused by the expansion of the universe. Additionally, it's unnecessary to differentiate between peculiar and recession velocities. Everything happening inside the box can be seen as a dynamic journey through space, much like what we observe in the lab. Within a compact cosmic space, we apply familiar everyday physics, enabling us to uncover the effects of expansion easily. We can utilize Newtonian mechanics to evaluate the expansion by embedding a spherical cosmic box in Euclidean space. The fascinating physics behind a slowly expanding box with non-absorbing walls is thoroughly understood, and this insight is readily applicable in the field of cosmology. A gas that is evenly spread throughout the universe is a great example. It acts just like a sample of gas in a cell that's gradually expanding. Understanding the behavior of gases in developing cells provides insight into how they behave when evenly spread across an expanding universe. The cosmic box encapsulates the universe in a nutshell. To understand what occurs universally, we only need to focus on a compact area enclosed by perfectly reflecting walls. Imagine a particle cruising through the vastness of an expanding universe. It moves effortlessly, liberated from the limits of a gravitationally bound system, much like a galaxy. It showcases some fascinating movements as seen by a local observer who is at rest in the expanding universe. Interestingly, this freely moving particle gradually loses its unique motion. It decelerates and ultimately comes to a standstill in the expanding universe. Every freely moving particle, including galaxies that aren't part of clusters, gradually loses its unique motion and eventually comes to a standstill in an ever-expanding universe. Let's dive into the intriguing scenario of a moving particle within an expanding box. The cosmic box needs to be compact enough so that the walls expand at a pace slower than the particle, allowing the particle to bounce back repeatedly from the widening walls. A particle gliding through the vastness of the universe moves along a straight path. The growing areas it traverses are precisely the same as the regions within the cosmic box at every moment in time. The speed it maintains in the box matches its speed when it's cruising freely in a straight line outside. The particle within the box constantly shifts its direction, yet it behaves just like it does when it's outside. The straight-line path is essentially tucked away within the confines of the box, and the bouncing particle maintains consistent speed and energy at every moment, as if the reflecting walls were never there. When a tennis player sprints forward to hit the ball, it zips across the court with greater speed and power compared to when they move backwards. In a fascinating scenario, a particle energetically bounces back and forth within a box that is either contracting or expanding, gaining or losing energy with each impact against the approaching or receding walls. The particle glides effortlessly in a direction that's perfectly perpendicular to the two opposing walls of a box that's expanding before our eyes. Typically, the particle bounces off in various directions. Yet, the outcome remains unchanged. The walls act as ideal reflectors, meaning that about the wall, the particle bounces back with the same speed it had upon impact. When the collision occurs, the motion flips in direction, yet the speed of the wall stays the same. As the walls pull back, the particle makes its way back to the center of the box, but with a bit less speed than before. Every time the particle hits a wall that's moving away, it bounces back with less speed. This principle applies not just to particles within an expanding box, but also to those freely moving in an expanding universe. Interestingly, the equation of motion from general relativity for a freely moving particle in the uniformly curved space of an expanding universe yields the same outcome. This demonstrates how the cosmic box enhances our understanding of events and enables us to employ straightforward methods to achieve key outcomes. At redshift z equals 1, when the universe is at half its current size, a freely moving non-relativistic particle's energy is 4 times what it is today. In contrast, a relativistic particle's energy is double its present value. Illuminating the fascinating world of light waves, the cosmic box reveals fascinating insights into why light diminishes energy as the universe expands. Every time light bounces off a wall that's moving away, it experiences a subtle redshift because of the Doppler effect. Back in 1913, Max Planck revealed something fascinating. The cumulative effect of repeated small Doppler redshifts in a uniformly expanding box follows a remarkable law where wavelengths increase in proportion to L. As L gradually increases, every wavelength experiences a stretch. Another fascinating perspective is to view light and all forms of electromagnetic radiation as composed of photons. These are particles zipping along at the speed of light with energy that matches their frequency. How cool is that? A photon can be seen as a relativistic particle, meaning its energy must change by 1/r. The relationship between frequency and wavelength reveals that as the scaling factor r increases, the wavelength also expands. This concept is relevant to all particles traveling at the speed of light, including neutrinos. In a universe that's constantly expanding, neutrinos shed energy just like photons do. Heat levels. The true potential of the cosmic box comes to life when we dive into the fascinating world of thermodynamics. In thermodynamics, we explore the intriguing properties of heat within isolated systems across a variety of conditions. What happens to a uniformly distributed gas in the context of an expanding universe? By isolating some of it in an ever-expanding cosmic box, we can tap into thermodynamics to enhance our understanding of cosmology. A system composed of particles in thermal equilibrium exhibits a uniform temperature throughout its entire volume. The particles are constantly on the move, darting in all directions at different speeds, and their average energy remains consistent throughout. Temperature represents the level of thermal energy present. Blackbody radiation, which occurs when radiation is in thermal equilibrium, is made up of photons with a range of energies. Interestingly, their average energy is uniform throughout and directly related to temperature. We've already discovered that when individual particles are allowed to move freely within an expanding box, they end up losing their energy. Exactly. A gas made up of numerous particles experiences the same phenomenon. Gas particles are in a constant state of collision with each other. The initial principle of thermodynamics: the walls of the cosmic box are designed to be perfectly reflective, ensuring that nothing can escape, including heat and all other forms of energy. The box functions as a self-contained system that maintains its energy without any exchange across its borders. The entire universe operates in an adiabatic manner. Every representative region maintains an adiabatic state, as an equal influx of incoming energy perfectly balances the energy exiting. The first law of thermodynamics is an intriguing concept that can be explored through two distinct parts. The initial segment explains that when energy flows into a closed space, it boosts the energy that's already present within that space. Since a cosmic box is adiabatic, with no energy entering or leaving, we can set aside this initial aspect and focus solely on the adiabatic system. The second part emphasizes that the work done by pressure consistently diminishes the energy within an expanding volume. One iconic illustration is the steam engine. The steam inside a cylinder pushes against the piston, and as it expands and drives the piston outward, it performs work while also losing energy through cooling. The cosmic box experiences pressure on its inner walls, leading to a decrease in contained energy as it expands. This suggests that, in our ever-expanding universe, energy is on a downward trend. The second law of thermodynamics. The second law of thermodynamics tells us that in an isolated system, entropy is always on the rise or stays the same. While it's possible to imagine perfect systems where entropy remains constant, these are merely theoretical concepts. The ultimate system we see in nature is the universe itself, yet even it has its flaws. Stars create entropy, and as a result, the entropy of the universe keeps on rising. Energy continuously transforms into less functional and practical forms, which means that entropy is always on the rise. In reality, you can't simply take the heat thrown away by your neighbor's house to warm up your own to the same level. This is because during the process, some energy escapes into the environment, and the heat from your neighbor is at a lower temperature. The cosmic box operates under adiabatic conditions, meaning no energy flows in or out. This raises an intriguing question. How can entropy rise in such a completely isolated system? The isolated system, a fascinating slice of the universe, is home to stars, which play a crucial role as the primary generators of entropy. Hydrogen ignites, creating helium, while nuclear energy is converted into heat. In the core, energy bursts forth at a staggering temperature of millions of Kelvin while it radiates from the surface at a much cooler temperature of thousands of Kelvin. Stars harness energy at scorching temperatures and release it when things cool down. They truly are fascinating entropy-generating machines. They release radiation into the cosmos, and the starlight present serves as a gauge for the entropy they produce. A significant portion of the universe's entropy is found in the radiation that permeates space. Every single thing in the universe emits radiation, including those mysterious black holes, and the fascinating concept of entropy is always on the rise. Straightforwardly, measuring entropy in cosmology boils down to counting photons. The total number n of photons in the cosmic box, when multiplied by the Boltzmann constant k, results in nk, serving as an approximate measure of its total entropy. I'm unable to efficiently heat my home using the warmth from my neighbor's discarded waste, as a portion of it escapes into the environment. The environment emits this heat into space as infrared photons. The universe takes note of my struggle to harness the discarded heat from my neighbor, reflected in a rise in the number of photons. Get ready for an exciting twist. The cosmic background radiation at 2.7 kelvins boasts a staggering number of photons, at least 10,000 times more than all the photons emitted by stars combined. A significant portion of the universe's entropy is already found in cosmic background radiation. The actions of stars have little impact on the overall entropy. A captivating theme in science during the first half of the 20th century was the eventual heat death of the universe, where everything would eventually fade and die, and how entropy would inevitably rise to its maximum value. It's fascinating to realize that the heat death happened ages ago, and here we are in a universe that's almost reached its peak entropy. A simple method to gauge cosmic entropy involves counting photons and nucleons and then calculating the ratio between these two. The universe is packed with fascinating numbers, averaging about 1 atomic nucleon for every cubic meter. When you throw in around 400 photons per cubic centimeter, this creates an intriguing ratio that falls between 10 to the power of 8 and 10 to the power of 9. Isn't that mind-blowing? Did you know that the universe has a specific entropy of nearly 1 billion photons per nucleon? It's a fascinating concept that highlights the complexity of our cosmos. The particular entropy remains relatively stable during expansion, suggesting that either the universe began with a significant initial reservoir of entropy, a high-temperature Big Bang, or that entropy was produced in the very early moments of the Big Bang. A key benefit of the significant bang type of universe is that it allows us to observe how specific entropy shapes the universe's characteristics. If the particular entropy had been significantly smaller, nearly all hydrogen would have transformed into helium during the Big Bang. Conversely, if it had been much larger, the universe would have been too hot for galaxies to form. In the first scenario, stars wouldn't shine brightly for extended periods, and in the second, stars wouldn't even exist. As the universe expands, energy is lost from various sources, including galaxies and thermal radiation, such as neutrinos. Where does all this energy end up? We take it for granted that light is redshifted and overlook the destination of its energy. It's clear to see how an expanding box can lose energy.
As light rays and particles push against the walls, they create pressure. When the box expands, this pressure does work, leading to a decrease in the energy of those rays and particles. Numerous engines utilize this principle. Steam engines and internal combustion engines are well-known examples of how pressure on a piston generates mechanical energy, while sacrificing heat energy within the cylinder. The cosmic box holds a fascinating snapshot of the universe, with its contents mirroring the state of the outside world at all times. Light beams and particles exert pressure against the inner walls, while corresponding rays and particles apply an equal force on the outer walls in response. The rays and particles within lose energy as they interact with the receding walls, which in turn causes them to exert pressure on the rays and particles outside. However, the energy lost by those inside is not replenished by those outside. And similarly, those outside do not benefit from the energy lost by those inside. To delve into what's unfolding, we revisit the segmented universe of numerous cells. In every growing cell, there's a gradual energy loss that neighboring cells can't recover, as they're also in the process of expanding and losing energy. The forces at play within cells are constantly in conflict, resulting in the loss of energy throughout. Yet, this energy ultimately finds its way back into practical applications. The universe is nothing like a steam engine, and we should never rush to the conclusion that pressure drives expansion. The expansion of the universe isn't influenced by pressure at all. The universe has the potential to contract, and in the future, it might transition from its current state of expansion into a phase of contraction. Imagine if the universe had a cosmic edge. The dynamics would shift dramatically. The pressure at that edge could perform work, transforming our universe into something akin to a steam engine. Yet the universe is boundless, and the pressure present throughout is consequently unable to generate mechanical energy. Our findings lead us to the exciting conclusion that energy in the universe is not conserved. The world we know is filled with a variety of elements, each defined by unique boundaries and gradients that set them apart from each other. Energy moves across these boundaries or along these gradients. Whenever energy is diminished in one area of our familiar world, it resurfaces somewhere else, either in its original form or transformed into another type, like mechanical energy. Some of the energy we consume inevitably escapes into the atmosphere and oceans, often seen as a loss that ultimately balances our energy budget. In closed systems, energy remains constant. Yet, the energy that flows out from these systems into the vastness of outer space isn't conserved and will gradually fade away, as the expanding universe isn't a confined system. Science holds firmly to the core principles and concepts of conservation, with the conservation of energy principle standing out as the most important. Whenever scientists notice that energy has seemingly disappeared, they embark on a quest to uncover its return in another form. These intriguing searches have historically resulted in the discovery of new and previously unrecognized types of energy. The discovery of the neutrino stands out as a quintessential example. When radioactive nuclei decay, they transition into lower energy states. Back in the 1920s, scientists discovered that the electrons emitted during this process didn't account for all the energy that was released. In 1931, Wolfgang Pauli, the brilliant mind behind the exclusion principle, which states that no more than 2 electrons can share the same waveform in an atom, proposed the existence of an undetected particle emitted during radioactive decay, one that accounts for the elusive missing energy. Enrico Fermi soon dubbed the imagined particle the neutrino. The neutrino made its exciting debut in experimental findings back in 1956. The conservation of energy principle is a fundamental concept that applies across various scientific fields, except in cosmology. We can explore the fascinating flow and interaction of energy in its numerous forms, asserting that it remains conserved in areas that don't expand with the universe due to its higher density compared to the average density of the cosmos. However, when we look at the universe as a whole, it doesn't remain constant. In an expanding universe, the total energy takes a dip, while in a contracting universe, it experiences a boost. What happens to the energy in our ever-expanding universe? So where does it originate in a universe that's contracting? The answer is nowhere, as energy in the cosmos is not conserved. The cosmic box offers an engaging glimpse into the fascinating ways things evolve in our ever-expanding universe. We don't stress about the curvature of space, because in a small enough area, we can always treat space as flat. There's no need to differentiate between the unique motion through space and the co-moving motion in an expanding universe. This is because the recession velocity of the walls is so small compared to the speed of light that the two types of motion become indistinguishable. We don't need to differentiate between Doppler and expansion redshifts. Additionally, we can utilize all the well-known principles of science that dictate how things behave in isolated expanding systems. Imagine a scenario where a cosmological challenge remains unsolvable using the cosmic box. In that scenario, the answer will likely revolve around curvature, the differences between peculiar and recession velocities, and the contrast between Doppler and expansion redshifts. Imagine this scenario. Albert is an observer outside the cosmic box, while Bertha is experiencing everything from within. This setup highlights the fascinating convenience of the cosmic box. Albert, out in the open, attempts to gauge the radiation he absorbs from every corner of the universe. He combines the contributions from various sources throughout, considering their distances in the ever-expanding curved space, their redshifts, and the absorption of their light as it travels through this curved space. He must also stay vigilant about the chance of rays making their way around in a closed universe. Picture his astonishment when, after completing this painstaking calculation, he discovers that the outcome remains unaffected by the universe's spatial curvature. Inside the cosmic box, Bertha finds the total light emitted by nearby sources, adjusts for absorption losses, and, through a much simpler approach, arrives at the same conclusion as Albert. She is completely unfazed by the fact that her result stands apart from the curvature of space. Albert is tackling the challenging task of evaluating double integral equations outside, while Bertha is handling the simpler, more straightforward problem of solving standard differential equations that are frequently encountered in physics inside. Once, the brilliant phytochemist Nernst contemplated a profound mystery within the physical sciences: the notion that all forms of energy in nature ultimately transform into heat, leading to an aging universe with no apparent signs of renewal. He devised a clever scheme that proposed a way to reconvert heat back into matter, suggesting a periodic universe where the concepts of beginning and end could be transcended. In his excitement, he reached out to Einstein, with whom he shared a complex relationship, scientifically collaborative, yet personally tumultuous. Nernst sought Einstein's thoughts on his visionary theory of the universe's evolution over billions of years. Einstein's response was, "I was not present." Physics and astronomy share a fascinating narrative. The second law of thermodynamics, a fundamental principle in physics, suggests a chilling fate for the universe. It predicts a heat death, where energy is uniformly distributed and all substances reach the same incredibly low temperature, rendering life impossible. The path to this final state may vary, but ultimately all roads converge on the same conclusion: universal death. This implies that barring any significant scientific errors, nature offers only two outcomes: progress or death. The only pause allowed is in the stillness of the grave. Some scientists, though not a large number, challenge this perspective. They acknowledge that current stars are dissipating into radiation, yet they propose that in the far reaches of space, this radiation might be reassembling into matter. They suggest that a new heaven and earth could be forming from the radiation released by the combustion of the old, rather than from its remnants. This idea supports what could be termed a cyclic universe. As one part fades away, the remnants of its demise are actively fostering new existence elsewhere. This notion of a cyclic universe stands in stark contrast to the well-established principle of the second law of thermodynamics, which asserts that entropy must continuously rise, rendering cyclic universes impossible, much like perpetual motion machines. In this fascinating exploration of the cosmos, we take a moment to look in every direction and come to the incredible realization that we are peering out to the very edge of the visible universe. We are diving into the Big Bang. We witness it stretching across the entire sky, just as it appeared in its final moments during the decoupling epoch. The radiation originating from the Big Bang has been wonderfully redshifted through expansion into the far infrared, making it invisible to the naked eye. The wall, while unseen, is something significant. The majority of photons in the universe are part of the cosmic background radiation that has persisted since the Big Bang. Their total number stays steady, and the universe's entropy is also almost unchanged. The entropy per unit volume, denoted as S, is equal to 4/3 T, multiplied by the thermal energy AT to the 4th power per unit volume, with T representing temperature. A represents a constant related to radiation energy density, leading us to the conclusion that S is equal to 4AT cubed divided by 3. Therefore, S equals T cubed remains stable, and since T changes with V, 1 equals 3, the overall entropy, SSV within volume V, remains unchanged throughout the expansion. The thermal radiation energy in V, represented as a T to the 4th power V, decreases at the same rate as T and is proportional to 1V to the 1/3 power. The energy in the cosmic background radiation, which was once vast, is now quite minimal. What happened to all this energy? Can you devise a response that maintains the overall energy balance? Do you think the second law of thermodynamics serves as a more effective conservation principle in cosmology compared to the well-known conservation of energy principle? Before the 20th century, the prevailing belief among Europeans and those of European descent was that the universe came into existence just a few thousand years ago, or perhaps a few 100,000 years at most. In the 18th and 19th centuries, a more radical group of thinkers believed that the Newtonian universe was in a constant state, where everything remained eternally the same, and the stars would shine forever. The discovery in the late 19th century that stars possess limited energy resources marked the conclusion of the belief in a constantly unchanging universe. In 1917, Einstein crafted a brilliant static universe through his groundbreaking theory of general relativity. In this universe, just like in all the fascinating universes we explore, every location shares similarities and matter is spread out evenly throughout. Space and time in the groundbreaking theory of general relativity have finally emerged from their slumber, stepping into the spotlight as dynamic forces in the universe. Einstein, convinced that the universe was unchanging, calmed space-time using a balancing force. In his 1917 paper, Cosmological Considerations on the General Theory of Relativity, he wrote, "I shall conduct the reader over the road I have myself travelled, rather a rough and winding road, because otherwise I cannot hope that he will take much interest in the result at the end of the journey." The conclusion that I shall arrive at is that the field equations of gravitation that I have championed hitherto still need a slight modification. The modification that he referred to was the introduction of the cosmological constant A. When this new constant is positive, it acts as an anti-gravitational force that leaves unaffected the curvature of space. A universe made static at one moment, however, is not necessarily static at earlier and later moments. To ensure that the universe remains static, in a state of permanent equilibrium, the curvature of space must be positive. The static Einstein universe, therefore, has spherical space. It is closed and finite and contains a mysterious force that opposes the attraction of gravity. In the Einstein universe, when we measure distances in light travel time, the radius of space's curvature is represented by the scaling factor r. If you think about it, the distance around the universe, or how long it takes for a light ray to make a complete journey, is 21r. Meanwhile, if you're standing at one point in this spherical universe, the antipode, essentially the point directly opposite you, is located at a distance of 1r. Imagine a static spherical universe that, when perfectly smooth, functions like a colossal lens. As an object moves away, it initially seems to shrink in the usual manner. However, once it reaches the halfway point to the opposite sedice, something fascinating happens. It stops getting smaller and starts to appear larger as it continues to recede. This unique perspective allows us to perceive objects in the antipodal region as if they were right next to us. We see those on. When we measure density in grams per cubic centimeter, we find that the circumnavigation time is approximately 4 = p hours, where g is the universal constant of gravity. Water has a density of 1 gram per cubic centimeter, and in a universe filled with transparent water, the time light takes to circulate once is 2 hours. In this hydrocosmos, which is smaller than the solar system and has a radius of curvature r of about 20 light minutes, antipodal objects are seen as they were 1 hour ago, and observers see themselves as they were 2 hours ago. Light repeatedly circulates, and the bemused inhabitants are reminded of what they were doing 2 hours ago, 4 hours ago, 6 hours ago, and so on. These Einsteinian creatures see their past in graphic detail and are deprived of the convenience of short memories. The navigation time in an Einstein universe, filled with a gas whose density is equal to that of our atmosphere, is slightly more than 60 hours. When the density is considerably less, the inhabitants observe the ghostly antics of their ancestors. In 1930, Arthur Eddington revealed that the Einstein universe is a precarious place where its residents must be cautious and speak softly. It teeters on a knife's edge. A slight push in one direction leads to gravity taking over, resulting in a big bang in a time frame akin to a circumnavigation period. A gentle nudge the other way allows the repulsive A force to take charge, and the universe, with its endless future horizons and echoes of the past, follows what some of its inhabitants might dismissively refer to as the principle of cosmological monotony. Static universes in a steady state neither expand nor collapse, and their contents, on average, never seem to change. These types of universes have appeared frequently throughout the history of cosmology. They often thrive in great empires experiencing decline, where individuals yearn for the enduring glory of the past, supported by aristocracies made up of generations of privilege. Interestingly, the last of these static, steady-state universes was conceived at the University of Chicago in 1918 and further developed in the 1920s by the astronomer William Macmillan, 1861-1948. The primary challenge that confronts any: imagine a universe that's always shining, where the stars never fade. The light from these celestial bodies streams out into the vastness of space, ensuring that the night sky is never truly dark. This intriguing mystery, the enigma of the night sky's darkness, sparked Macmillan's groundbreaking idea that atoms are created in the depths of space through radiant energy. He introduced a theory suggesting that stars emerge from interstellar gas, evolve, and gradually lose their mass as they. Macmillan's perpetual motion universe captured the imagination of many. It found a champion in the renowned physicist Robert Millikan, celebrated for his groundbreaking measurement of the electric charge of an electron in 1905. Millikan was convinced that cosmic rays, identified in 1911 by Victor Hess, represented the birth cry of newly formed matter in the vastness of space, serving as evidence that the Creator is still on the job. We know now that a star radiates away at most only 1% of its mass in its luminous lifetime on the main sequence, and cannot dissolve away into anything in the manner proposed by Macmillan. A star has a fixed number of baryons, in this case, nucleons. However much it radiates at the expense of its nuclear and gravitational energy, the number of baryons remains constant, apart from particles escaping from the surface, and the star cannot dissolve entirely into radiation. We also know that matter cannot be recycled in the ingenious way proposed by Macmillan. Highly energetic radiation is capable of creating particles and antiparticles, particle pairs, and not just particles by themselves. And these particle pairs then annihilate and convert back into radiation. Most starlight in space is far too weak to create particle pairs. While Macmillan's static universe conserves total energy, it undoubtedly does not conserve total entropy. A static, steady state of conserved entropy exists only in a universe in perfect thermal equilibrium, in which there are no galaxies, stars, or planets, and also no arrow of time, and hence no way of distinguishing the past from the future. And, of course, there are no inhabitants. The last static, steady-state universe enjoyed fame until the 1930s, when it was confronted with growing evidence of an expanding universe. It quietly faded away. The de Sitter universe, introduced in 1917, the same year Einstein put forth his static universe, was initially seen as a challenge to Einstein's cosmological theory. It featured flat space and seemed somewhat nonsensical, since it lacked matter. A Euclidean geometry devoid of matter shouldn't display any peculiar characteristics. Yet, to our astonishment, the addition of the cosmological term A breathes life into it. The de Sitter universe maintains a steady state, characterized by constant Hubble and deceleration terms, where nothing seems to change in the absence of matter. The term steady-state universe is typically associated with the model introduced by Hermann Bondi, Thomas Gold, and Fred Hoyle, which expands similarly to the de Sitter universe, but includes matter. In this model, new matter is continuously created, replenishing rather than diluting the existing matter through expansion. It's important to note that other universes, such as the de Sitter and Macmillan units, also exhibit stability. The prominent cosmological models began with the Einstein universe, characterized by matter at rest, and the de Sitter universe, defined by motion devoid of matter. In a groundbreaking development during 1927 and 1931, the Belgian cosmologist Georges Lemaître unveiled the general cosmological equations, which had been initially discovered and published by the Russian scientist Alexander Friedmann in 1922 and 1924, but had been overlooked. This pivotal moment marked the dawn of a new era in cosmology. In the fascinating realm of Friedmann family universes, we explore models where the A-force is set aside and treated as if it were zero. There are three fundamental types of Friedmann universes: each linked to the curvature constant k, with values of 0, 1, and 1. Alexander Friedmann, 1888 to 1925, a Russian scientist of many interests, was a professor of mathematics at the University of Leningrad. According to George Gamow, a former Friedmann student, Friedmann spotted an error in Einstein's 1917 cosmology paper. The introduction of the A-force led Einstein to conclude that the universe is necessarily static. Friedmann wrote to Einstein about his own more general treatment, but received no reply. Through a colleague visiting Berlin, Friedmann succeeded in obtaining from Einstein a grumpy letter agreeing with his conclusions. Friedmann then published an article on the curvature of space in 1922 in the German journal Zeitschrift für Physik. A second article on the possibility of a world with constant negative curvature appeared in the same journal in 1924. The discovery of extragalactic redshifts made both articles timely. But unfortunately, Friedmann's work went unnoticed and had no influence on contemporary cosmology. In honor of Friedmann's pioneering work, we refer to uniform expanding universes of zero cosmological constant. Universes that kick off and wrap up with big bangs were once known as oscillating universes. The idea was that since the universe expanded, much like a phoenix rising from the ashes of one big bang, it would also emerge from the next big bang, and so forth, bouncing back and forth in an endless cycle. This concept suggests that the universe has already undergone countless oscillations, perhaps even infinite ones, and will continue oscillating indefinitely into the future. What we once believed too. In the early 1930s, Richard Tolman made groundbreaking discoveries that revealed a fascinating truth about the universe. Each oscillation period is never precisely the same as the one before it. As stars and other luminous sources emit radiation, the number of photons in space steadily rises with each cycle. This means that the radiation, or entropy, in one cycle is always more than in the last. Even though a Big Bang is a cataclysmic event that wipes out all structural detail, we can see. The cosmic background radiation, currently at a chilly 3 Kelvin, is set to rise in temperature over future cycles. Eventually, this will lead to a time when galaxies cease to form and stars fade away. In these future cycles, devoid of stars, the increase in radiation will slow down significantly, and the oscillations will change at a glacial pace. Life, as we know it, will no longer exist. Historically, the fringe was more fabulous, with most hydrogen transforming into helium during each event. This means oscillating universes are an intriguing topic that sparks curiosity, but we should approach the concept of a universe maintaining its core identity through multiple Big Bangs with caution. The ultimate fate of a Big Bang, when the universe returns to its incomprehensible primordial state, remains a mystery. One certainty is that the universe retains its topology. If it's spatially closed, it stays closed, and if it's open, it remains open. A finite universe cannot transform into an infinite one. Imagine a cosmic genie hiding in the depths of the primordial Big Bang, creating countless universes, each with its own set of fascinating laws and fundamental constants. What emerges from a Big Bang could be utterly unrelated to what initially sparked it. Friedmann, Lemaître. Universes. Georges Lemaître. Georges Lemaître, 1894-1966, was ordained as a priest in 1922. In 1927, the same year he earned his doctorate from the University of Leuven, he published a groundbreaking work on the expansion of the universe in Belgium. During the late 1920s, as debates raged over the merits of the Einstein and de Sitter universes, Lemaître's contributions initially went unnoticed, until Eddington highlighted them by facilitating their translation into English. Lemaître was the pioneer who proposed an initial high-density state known as the primeval atom, earning him the title of the father of the Big Bang. He brought back to light the cosmological equations initially formulated by Friedmann, and we will refer to these broader equations, which incorporate the cosmological constant, as the Friedmann-Lemaître equations. Lemaître singled out from the many solutions of the Friedmann-Lemaître equations a closed universe, K positive, containing a repulsive force, A positive. This universe has the same basic ingredients as the Einstein universe, with the critical difference that A is slightly greater than the value chosen by Einstein, and the Lemaître universe, therefore, cannot attain a static state. It starts as a Big Bang and evolves through two stages of expansion. In the first stage, expansion decelerates because gravity is stronger than the repulsion of the A force, and the radius of the universe slowly approaches the Einstein radius. Expansion in the second stage accelerates because the repulsion of the A force is now more substantial than the attraction of gravity. The Lemaître universe begins as a Big Bang, finally becomes a whimper, and in between hesitates and loiters as a sort of Einstein universe. It neatly combines the properties of the rival Einstein and de Sitter universes. It is closed and has cosmic repulsion like the Einstein universe. Under the urge of the repulsion force, it expands into a whimper like the de Sitter universe. Lemaître thought that galaxies formed during the hesitation era. Lemaître's hesitation universe captured the imagination of many and had something intriguing for everyone. Its standout feature was that during the second stage, its age surpassed the Hubble period. By fine-tuning the cosmological constant to exceed the Einstein value slightly, we can significantly prolong the hesitation or loitering phase. Until the 1950s, cosmologists believed the Hubble period was 2 billion years, making a universe with an extended age due to delayed expansion quite appealing. However, later adjustments to the value of h diminished the allure of the Lemaître universe. Back in the late 1960s, scientists brought the Lemaître universe back into the spotlight to tackle the mystery of why quasars seem to cluster around a redshift value of 2. The theory suggested that these fascinating objects emerged during a prolonged hesitation phase, with a maximum redshift of 2, due to the universe's radius being only 1/3 of what it is today. Since then, a plethora of quasars have been discovered, and the clustering of redshifts at Z2 has become notably less significant. Many quasars now exhibit redshifts far exceeding 2, and the case for a hesitation era appears less compelling. The challenge with a prolonged hesitation period lies in the inherent instability reminiscent of the Einstein universe. This hesitation period has been characterized as a time dominated by titans, where galaxies come into existence and quasars hold sway, an epoch filled with dramatic events that reverberate throughout the cosmos. Therefore, hesitation cannot meaningfully prolong the age of the universe. The universe of Eddington. Lemaître was probably drawn to the intriguing implications of a Big Bang for creation because of his religious convictions. However, Eddington thought the Big Bang theory was visually unappealing and found the impact of creation off-putting. Every man dedicated himself to the customs of his religion. The bangers, who have bangers e-lead, and the anti-bangers, who are a minority, are still the two main cosmological groups. Eddington questioned the notion that the universe began abruptly in 1930, stating his belief that evolution is allowed an infinite time to get started, a necessary condition for the universe to have a beginning. A fascinating closed system with a cosmological constant equal to Einstein's value, is the Eddington universe. For an infinite or at least indefinite amount of time, it begins as a static Einstein universe. It then awakens from its protracted sleep and starts to enlarge as a result of sporadic disruptions. In the Einstein state, where gravity and repulsion are perfectly balanced, it exists in a nascent form. It might collapse, creating a universe that is no longer ours. Later on, it changes into the dynamic de Sitter state, where gravity is subordinated to repulsion. The Eddington universe combines the intriguing ideas of the Einstein and de Sitter universes that once enthralled cosmologists, much like the Lemaître universe. Eddington discovered the fascinating instability of Einstein's universe, and it's fantastic that he initially endorsed the notion that the universe could be unstable and exist for an interminably long period. Around 10 billion years ago, a world that lay in wait came to life in a universe where no galaxies formed and life remained dormant. What an intriguing realization. Eddington was forced to refute the eerie notion of a primordial beginning by implying a night or an infinitely long past. Among modern cosmologists who were repelled by the idea of cosmic birth and death, he was the first, but by no means the last, voice. His ideal world is in a dreamlike state. It awakens, develops gracefully, and ends with a gentle sigh. However, as revealed by St. Augustine of Hippo in the 4th century, the inexorable principle of cosmogenesis remains unavoidable, regardless of how one handles the complexities. Creation is an essential component of our universe, not merely a historical occurrence. Similar to space, time is entwined with the universe, whether it is infinite or finite, and both were created simultaneously. The containment principle is now the basis for the Augustinian law of cosmogenesis. There is a striking similarity between Lemaître's and Eddington's worlds. They serve as a standard by which to measure everything in the universe, because they maintain the cosmological constant. How does the size of particles get determined? How are the values of the fundamental constants determined? And how do infinite universes display K0 or K1? During a cosmological discussion titled Evolution of the Universe at a British Association meeting in 1931, Birmingham's Bishop, Ernest Barnes, emphasized a crucial topological distinction between finite and endless space as a classification method. He expressed the viewpoint that our space is finite, yet unbounded. Just scandal to human thought, because we could only hope to understand the range of God's activity by thinking about the universe. The question of whether a universe is expanding, static, or collapsing arises because the kinematic classification system ignores geometric and dynamic factors. We have already called this the bang and whimper idea, and now we will extend this concept to include both static and oscillating states. A star's pressure gradient resists the force of gravity. As you approach the star's center, pressure increases, creating this outward force. The idea is essential, much like how a pressure differential can force water through a pipe or move a piston in a steam engine. However, there is no pressure differential, and, as a result, no forces at work in a uniform universe, where everything is the same, and pressures are constant everywhere. Considering that there is no net force generated on a cosmic scale, have you ever wondered how the pressure in the universe affects its expansion? The thought is intriguing. In essence, pressure is an energy, and this energy, along with its mass equivalent, is what creates gravity. Imagine a gas-filled sealed vessel. The pressure rises as the gas molecules move more quickly due to the heat. There is another way we can explain this rise in pressure. We measure the importance of pressure in the intriguing field of cosmology by its corresponding energy density. It's interesting to note that the non-relativistic formula for sound speed in a fluid is relatively simple. The sound speed in gases is very similar to the average particle speed, which is usually much slower than the speed of light. In cosmology, pressure is frequently regarded as insignificant. However, pressure was an essential factor because particles raced at relativistic speeds in the early universe due to its extremely high temperatures. We find the maximum pressure for a given energy density in universes that are entirely composed of radiation. The pressure is 1/3 of the energy density when the radiation is uniformly distributed and the distributed flux is isotropic. Richard Tolman made an intriguing discovery about the universe in the early 1930s. He discovered that the behavior of a universe entirely composed of radiation is comparable to that of a universe containing low-pressure matter. There's a significant distinction, though. A radiation universe that has the same density as a matter universe decelerates more. This occurs because the expansion slows down more quickly than it would in a matter universe due to the intense radiation pressure acting as an additional source of gravity. We discovered that a closed Friedmann universe with zero pressure matter has a lifetime of 1/r max and expands to a maximum size, R max. It's interesting to note that a closed Friedmann universe made entirely of radiation has a finite lifetime and expands and collapses in a similar manner. It's interesting to note that pressure has an effect that deviates from our initial assumptions. The pressure would accelerate the expansion of the universe that is expanding. The relationship between the speeds of sound and light determines the importance of pressure or energy density. In contrast, pressure causes a more gradual expansion and a faster collapse in the real world, where sound moves more slowly. This unexpected result results from the absence of precedence in a uniform universe. Pressure only has a significant effect on the gravitational forces that govern the universe, because, unlike a boiler, the universe does not have universes to contain pressure. For example, the gravitational force produced by uniform radiation is twice that of matter with the same mass density, but zero pressure. With its flat space and lack of a cosmological constant, the Einstein de Sitter universe offers an intriguing framework for investigating the impact of pressure. The scaling factor R is interestingly proportional to T² in the case where it contains matter at zero pressure, where T is the time since the Big Bang. Let's go to a more relatable universe, one that is made up of both matter and radiation, like our own. Cosmic background radiation is the leading player in the radiation game, with radio waves and starlight coming in second and third. Since matter is currently 1,000 times denser than radiation, matter predominates in our universe. We discussed in Chapter 17 how the density of radiation shifts as 1/r to the fourth power, whereas the density of zero-pressure matter changes as 1/r to the third power. In retrospect, the radiation density exceeded that of matter when r was more than 1,000 times smaller. Long ago, at redshifts larger than 1,000, the universe was dominated by radiation. Early on, any universe with cosmic background radiation, no matter how small, went through a period of radiation dominance. Tension in universes. We delve into the fascinating field of negative pressure. The idea of negative pressure is initially shocking because we are all accustomed to positive pressure, which is found in steam engines and stars. In 1951, cosmologist William McCrea made the case that our everyday experiences do not rule out the possibility of cosmic tension or negative pressure in the universe. The behavior of galaxies, stars, and steam engines is not directly influenced by cosmic tension, which is uniform throughout the universe, but lacks gradients to pull things around. We recognize pressures when they act on moving walls, as in steam and internal combustion engines, and when they change from place to place, as in the Earth's atmosphere and oceans. However, Pressure has no discernible effect other than acting as a source of gravity when it is uniform, unconstrained, and devoid of gradients. Even if there is negative pressure, we cannot sense it unless it affects how the universe behaves. According to our explanation of the Einstein equation, matter is represented by the right side, while the left defines curved and active spacetime. The left side of the equation, however, is clear-cut. On the other hand, the ambiguity surrounding the exact meaning of matter in this context makes the right side unclear. On rare occasions, people have positioned remarkable items on the right side of the equation. Usually, only the density of matter, field energies, positive pressure, and well-known aspects of the outside world are kept constitutive. But since the universe exists outside of our familiar realm, we cannot compare it to a star or a steam engine. It is relatively unknown and frequently disregarded that there is a uniform cosmic stress with negative pressure that does not affect the structures of planets, stars, or galaxies. However, McCrea contended that we cannot rely on common experience to determine what should be on the right side of the Einstein equation in cosmology, because the universe might be governed by forces that are not directly observable in astronomical systems and laboratory experiments. As we have seen, the cosmological term significantly broadens the range of potential cosmological models, and we find that this range is further expanded by negative cosmic stress. Consider the tremendous consequences of negative pressure in a universe that is expanding. A universe under tension releases energy as it grows in this fascinating scenario. Imagine a single piece of elastic that represents the universe. When you stretch it, it warms up because the effort required to pull it produces thermal energy. This additional energy carries mass. A similar magic occurs in a universe with negative pressure. Energy is released as it expands and takes on exciting new forms, such as the formation of new particles. That is fascinating. Imagine a universe with an intriguing equation of state, where tension and energy density are equal. In this case, the energy released during expansion is sufficient to maintain a constant mass density. In this amazing situation, energy becomes matter, and the universe expands while keeping its density constant. The Bondi-Gold-Hoyle steady-state universe's ongoing matter creation is brilliantly explained by this idea, which McCrea first proposed. McCrea pointed out back in 1951 that all of Hoyle's findings can be derived within the framework of general relativity theory by simply changing the zero of absolute stress. This derivation offers a distinct and captivating physical coherence. Alan Guth's 1981 proposal introduced the term inflation to refer to expansion at constant density, and the intriguing notion of the false vacuum is connected to the inflation tension in the inflationary universe that Guth suggested. Embracing cosmic homogeneity, also known as the cosmological principle, would be much easier if we could understand the reasons behind its existence. The observed universe exhibits a striking isotropy, which leads us to the Copernican principle, suggesting that the universe is uniform, mainly everywhere. The concept of homogeneous vacuum, which holds that all places are alike at the same time, stands out as one of the most fascinating features of the universe. When we talk about explanations, we are inevitably thinking backwards, because causes always come before effects. Can we illuminate homogeneity by going back to a time when the universe was young, when physical processes turned chaos into order, like a storm giving way to a calm sea? This is the beginning of a big problem. The observable universe is roughly the size of the Hubble sphere, which has a radius of about 10 to the power of -1 billion light years. Light from objects farther away hasn't reached us, yet because the universe hasn't aged enough. Regions of the universe that are separated by distances larger than the Hubble length cannot affect each other. As we go back in time to find the origins of uniformity, the Hubble length decreases, allowing previously disconnected areas to interact. The expanding boundary of the Hubble sphere surpasses objects moving away at the speed of light and recedes at the same speed. In a decelerating universe, where the deceleration parameter is greater than 0, the Hubble sphere grows in the comoving frame, which implies that regions that can now interact within the Hubble sphere were previously isolated outside of it. If these regions are now able to connect, were once cut off from each other, how can we possibly understand homogeneity by searching for its origins in the past? This scenario is known as the horizon riddle. The idea of a decelerating universe restricts our capacity to offer a broad, large-scale explanation that depends on previous influences. The chaos school and the anti-chaos school are the two primary methods for solving the homogeneity riddle. In contrast to the apparent disorder seen in deterministic non-linear dynamical systems, such as the weather, the chaos school's mythological traditions imply that the universe begins formless and steeped in true chaos. According to mythology, there was indescribable chaos in the beginning, before heaven above and earth below was formed. Through this chaos and the influence of natural or supernatural forces, a state of order eventually emerged. Charles Misner from the University of Maryland has studied how uniformity can emerge from chaos. The chaoticists are tasked with addressing not only the homogeneity problem, but also intriguing questions, such as the origins of cosmic background radiation and the initial conditions that led to the formation of galaxies. In this fascinating story, the processes that produce homogeneity release energy, which heats the Big Bang, and cosmic background radiation serves as contemporary evidence of this dynamic. Because of the initial inhomogeneity, tiny density fluctuation, researchers have explored the intriguing world of homogeneous but anisotropic universes to investigate whether anisotropy can evolve into isotropy. These fascinating mixmaster universes have dramatic fluctuations, expanding in one direction while oscillating rapidly in the other two. Imagine a cylindrical body that extends along its axis, while its radius oscillates. Over time, in successive eras, each longer than the last, the directions of expansion and oscillation swap places. A crucial question is how much matter and radiation inside will lessen these convulsions through dissipative processes. Initially, it seemed that neutrinos from the early universe might help calm these fluctuations and promote isotropy. However, later studies have demonstrated that it is not possible to transition from a state of extreme unevenness to a uniform state. As a unifying factor, inflation resonates with the chaos theory viewpoint. Imagine a highly irregular surface that represents primordial chaos. Then, how do we make this surface smooth? In the context of inflation, we don't just smooth it out. Instead, we take a tiny area and inflate it to an incredible size, trillions of times larger. By stretching and fine-tuning its irregularities, we eventually create an expansive surface. In the very early universe, a state of tension causes rapid expansion, solving the homogeneity puzzle. Significant inhomogeneity probably existed on large scales before inflation, but a relatively homogeneous state appears on scales smaller than a Hubble length due to causal interactions. During inflation, the Hubble sphere's size stays constant. At the same time, its quasi-homogenized content expands rapidly, forming a much larger homogeneous region than the Hubble sphere itself, effectively stretching and smoothing out the initial irregularities. Once inflation stops and deceleration commences, the Hubble sphere begins to expand, surpassing regions of the universe that have already achieved a homogeneous state. Anti-chaos. The anti-chaos school proposes that the universe originates from a uniform state. This may seem like a trivial way to avoid the problem, but it is the result of deep reflection. We usually use the past to explain the nature of individual entities. Still, the universe is a cohesive whole that encompasses both space and time, which begs the question of whether it is appropriate to look for causes when attempting to understand its design. The universe is both time and space, so we shouldn't look for its design's cause in a particular time or location. Homogeneity may be necessary and crucial. Without it, the universe as we know it might not exist. And without it, our existence could be in danger, even if the universe itself were to endure. Back in 1973, C.B. Collins and Stephen Hawking wrote, "The fact that we have observed the universe to be isotropic is only a consequence of our existence." They investigated the possibility that an inhomogeneous universe might not have galaxies because of inappropriate initial conditions, which would prevent stars and life from forming. It's intriguing to consider that there may be a variety of universes, some homogeneous, some inhomogeneous, but that observers can only find success in the homogeneous ones. We've touched on hierarchical universes, which have been important in the development of cosmological thought. Other intriguing models suggest that, although these universes may seem homogeneous on scales smaller than Hubble's length, they reveal their inhomogeneous nature on grander scales. Imagine widely separated, unsynchronized universes that tracked in their unique rhythms. In this section, we examine a few of the fascinating inhomogeneous universes that have captivated cosmologists' attention. They may be in a state of contraction, collapsed regions within a shared space-time that form giant black holes lurking behind event horizons, and remote areas far out of our observational reach may not be in sync with our own. Suppose that the universe outside observes enormous hierarchies of black holes nested inside one another, each of which represents a domain of internal dynamics frozen in stasis. Our region's background radiation is remarkably uniform, and any ideas about inhomogeneity are now limited to far-off regions that are invisible to the naked eye. These isolated areas are at least 100,000 Hubble distances away because the universe is isotropic to a ratio of 1 part in 100,000. There might be unsynchronized areas thousands of trillions of light-years away, and perhaps even trillions of light-years away, if the universe is infinite in space. However, we currently lack the tools to verify this. In his quest to comprehend gravity, Milne journeyed across the Stoic universe. Oxford University cosmologist and renowned astrophysicist Edward Milne analyzed general relativity critically, but concluded that it was insufficient. In Kinematic Relativity, published in 1948, 2 years before his death, he wrote, "A geometry differing from the one commonly used in physics imposed credible notions of motion. The notion that gravitation was a distortion of space was a plausible one, but it provided no explanation for the nature or origin of gravitation. Why matter affects space was still an open question. According to Einstein's theory, geometry and matter are related, but Milne questioned whether this was true. Gravity is not a part of the original framework of Milne's intriguing theory of the universe, known as kinematic relativity. By applying a few fundamental concepts, including the laws of special relativity and the cosmological principle, he sought to gain a comprehensive understanding of the cosmos, elucidating the nature of gravity and other fundamental laws. He felt that rather than just giving detailed explanations of how things work, cosmology should also explain why things exist the way they do. Even though he might not have achieved his original goals, his work unquestionably made a significant impact on cosmology and demonstrated the value of his strategies and insights. When dissected into its most basic elements, Milne's picture of an expanding universe is much easier to understand than the intricacies of everyday life. Consider a vast universe composed of a spherical cloud of particles called galaxies, all of which are expanding within a flat, infinite space. It's an intriguing idea that begs for investigation and amazement. Imagine the traditional Stoic universe, with its center and edge redesigned to conform to special relativity. Particles are launched outward in all directions, at speeds ranging from 0 to almost the speed of light as the expansion begins at a particular location in space. The cloud's outer edge travels through space at a speed that is nearly equal to that of light. The recession velocities and distribution of all other particles are uniform and consistent within the frame of each particle. The Big Bang is no longer seen as a single point in space because of the relativity effect, which causes the majority of particles to congregate close to the cloud's edge, causing space to expand. After transforming Milne's picture into a dynamic universe with curved space, let's examine it more closely using general relativity. We take the cosmological constant A and set it to 0 in the Friedmann-Lemaître equations. Additionally, we set the gravitational constant G to 0, since Milne didn't require gravity on a cosmic level. In this fascinating framework of motions, known as kinematic relativity, Milne attempted to show that each particle, moving freely and unaffected by any force, exhibits behavior that mimics the effects of gravity. Milne defined our finite and bounded universe as one full of innumerable particles in the field of view of any observer, merging towards the limit of visibility into a continuous background. He set out to challenge the notion that gravity exists by examining the concept from a cosmic perspective. Many listeners were not persuaded by his arguments, and it remains unclear what his cosmological theory entails. Milne associated a galaxy with each particle. This universe has an infinite mass due to the infinity of particles at work. His constrained and contained universe can be mathematically transformed into an infinite and limitless one by changing the space and time intervals. Greetings from this fascinating new universe. It has homogeneous and isotropic expanding space and is based on the Robertson-Walker metric. This universe has a negative curvature and is uniformly populated with galaxies, resulting in an intriguing cosmic landscape. The galaxies are positioned as stationary due to this remarkable change in space and time, where t is the universe's age. The Hubble time corresponds to the universe's age, and the universe continues to expand. Milne's universe expands at a constant rate of 0 deceleration, loses its centers and edges, and has an infinite space of negative curvature when it is incorporated into the framework of general relativity. Hermann Bondi and Thomas Gold proposed the steady-state expanding universe in 1948. It is based on the perfect cosmological principle, which holds that all places are the same in space and time. An infinite age is claimed by a universe that is constantly expanding. Due to the difficulties that many evolutionary universes were facing at the time, the Hubble period seemed to be shorter than the age of the solar system. This feature of the model was particularly noteworthy in 1948. To maintain a constant density, an expanding universe that stays the same requires a steady stream of new matter. Thus, Bondi and Gold wrote, there must be a continuous creation of matter in space, at a rate that is, however, far too low for direct observation. This new matter appears to be created spontaneously rather than by radiation, as is the case in the static Macmillan steady-state universe. Throughout the history of science, the intriguing theme of spontaneous creation has repeatedly emerged. Even in the 20th century, there were many fascinating examples of spontaneous creation. The centers of the nebulae are akin to singular points where matter flows into our universe from an entirely different spatial dimension. To someone in our universe, these points seem like sites of continuous matter creation. In 1929, the famous the famous astronomer James Jeans suggested in his book Astronomy and Cosmogony that the centers of the nebulae are akin to singular points where matter flows into our universe from an entirely different spatial dimension. Jordan's drops were early-stage stars. He said, "The idea arises that the cosmic creation of matter doesn't occur as a scattered formation of protons, but rather through the abrupt emergence of complete drops of matter." A fascinating theory of continuous creation for a de sitter universe in which galactic embryos spontaneously emerge was being developed concurrently by Japanese mathematicians in Hiroshima. This innovative idea will enthrall listeners. A dynamic universe that is constantly expanding. The expanding steady-state universe's cosmic landscape is unaltered. Therefore, the density P, the deceleration term Q, the curvature K, and the Hubble term H must all remain constant. The formula for the curvature K is K equals R squared. As the scaling factor R increases with expansion, the curvature only stays constant when K is 0, indicating that space is flat and infinitely extensive. Given that R divided by R underscore is the value of the Hubble term, represented by the letter H. In a continuous model, RE is precisely proportional to R, and the scaling factor grows exponentially, which is similar to the de sitter universe's fascinating behavior. This ensures that the deceleration term will always remain at 1. For each Hubble period, a constant density requires the creation of matter at a rate of about 1 hydrogen atom per cubic meter, or about 1 galaxy per year for each Hubble sphere. Only a third of a Hubble period is needed for the steady-state universe to renew itself. Long-lived objects, such as galaxies and nucleons, typically have a lifetime of approximately 1/3 of a Hubble period. The average age of all galaxies is roughly 1/3 of a Hubble period, while some galaxies are young and have only recently formed. With a remarkable age of approximately 15 billion years, our galaxy is approximately twice as old as the average galaxy in the steady-state universe. The majority of galaxies in a Big Bang universe are remarkably similar in age, with an average age of 13.8 billion years. The fact that our galaxy is much older than the average galaxy, but coincidentally, exactly matches the age predicted in a Big Bang universe, is intriguing to someone who believes in a cosmic steady state. Fred Hoyle showed how the general relativity theory could be modified to accommodate the continuous creation of matter, following a lively discussion with Mr. T. Gold. Hoyle investigated the scalar tensor theory, which we will discuss in a moment, and found that the equation links the Hubble term and the universe's constant density in the same year that Bondi and Gold presented their steady-state theory. The question of the precise shape that matter takes during creation was left unanswered by Hoyle's creation theory. Using a mathematical tool, this theory questions the law of conservation of matter, a fundamental idea in general relativity. As we discussed earlier in this chapter, William McCrea proposed that cosmic tension, a cosmic tension that, when paired with energy density, sustains a state of constant density, is the source of continuous creation. Like Hoyle's theory, McCrea's theory fails to explain why creation only involves matter and not antimatter. According to Bondi and Gold's groundbreaking research, creation is a consistent occurrence throughout the universe, ultimately resulting in the condensation of newly formed matter into magnificent new galaxies. The creation process may not be uniform across space, but rather more dynamic in regions where matter is already present, according to a fascinating alternative theory put forth by McCrea in 1964. He proposed that all matter holds the potential to promote the creation of more matter. Typically, matter resides within galaxies, and the emergence of new matter usually fuels the expansion of these galaxies. Yet, there are times when a piece of matter breaks away from its galaxy. This fragment carries the potential to spark new creation. If it succeeds, it becomes the seed of a new galaxy. The steady-state theory has declined due to groundbreaking discoveries. The abundance of quasars from earlier times demonstrates the fantastic evolution of our universe, while the cosmic background radiation suggests a massive Big Bang event. Hoyle and Jayant Narlikar have boldly revived the semblance of the theory. To bolster the notion of an eternal universe, they highlight notable inhomogeneities and fluctuations in the laws and constants of nature. The expanding steady-state theory now has a place in history, but the original elegant simplicity that enthralled so many has faded. Dennis Sciama wrote in 1967, "I must add that for me, the loss of the steady-state theory has been a cause of immense sadness. The universe may be flawed, but we must adapt to its limitations." The steady-state theory has a sweep and beauty that for some unaccountable reason, the architect of the universe appears to have overlooked. The intriguing scalar tensor theory of gravity was first presented by Pascual Jordan of Germany in 1939. Let's review the fascinating idea of introducing a scalar field within the Riemannian spacetime of general relativity and look at how it can change from place to place. The scalar field has a unique effect on gravity, maintaining its dynamic curvature through an intriguing process known as conformal transformation. A conformal transformation, also known as a unit transformation, pushes the boundaries of general relativity and broadens the scope of physical theories. Let's imagine a universe in which all atoms are the same, and the gravitational constant g is a continuous universal value. We turn this ordinary universe into an amazing one, where the units of measurement vary by location and change over time, making it impossible to tell that some parts of the universe have been compressed while others have been stretched. As we travel with a clock and a ruler, we see that the masses of protons and electrons fluctuate, the gravitational constant exhibits variability, and matter undergoes creation and destruction. Jordan became intrigued by a scalar tensor theory after encountering Paul Dirac's large number hypothesis, which suggested that G diminishes in value as the universe expands. Jordan demonstrated that a scalar function could adjust G in a preferred manner. Initially, the control knobs were misaligned, leading to the creation of universes where everything had shifted in astonishing ways. G wasn't the only thing that varied, as Dirac suggested. C and M did, too. Matter seemed to appear and disappear, and particle masses fluctuated. Cosmologists generally show a reasonable openness to competing ideas, as long as they don't stretch the limits of belief too far. The concept of a shift in the gravity constant, the emergence of matter, or changes in subatomic masses, is certainly intriguing on its own. However, when two or even all three are combined, patience begins to wane. Despite Jordan's pioneering role in scalar tensor theory, his contributions to cosmology have not yielded significant results over time. Hoyle used the scalar tensor theory to create matter in a dynamic, constantly expanding, steady-state universe. A steady density was maintained by adjusting the creation knob C, but a mistake could cause changes in the creation rate, upsetting the equilibrium of a steady-state situation. Hoyle became well known as its most ardent supporter, and, along with Narlikar, modified the steady-state theory to bring it into line with the age of the universe, while departing from the notion of continuous creation. surprising discoveries have upended the steady-state theory. Robert Dicke explored Mach's principle through the lens of scalar tensor theory. Ernst Mach proposed that a particle's inertial mass arises from its interaction with all other particles in the universe, as if it is sensing their presence. Dicke proposed that this principle clarifies why the gravitational mass of a particle, defined by its reaction to a gravitational field, matches the inertial mass of the particle, which is defined by its response to acceleration. Typically, we set these two masses to be equal and denote them as m. However, what makes them equal? Dicke presented his argument in this way. Imagine m as the gravitational mass and L as the radius of the observable universe. Now, picture g(m)m grav equals L as the gravitational energy of just one particle. It is a fascinating concept. Dicke suggests that this energy is equivalent to (c²), aligning perfectly with the groundbreaking discovery of cosmic background radiation. One intriguing idea is that particle masses might evolve. The universe is believed to be static, with atoms, humans, and stars gradually shrinking in size as a result of the increasing mass of subatomic particles. The ever-evolving universe of atoms, which was once fixed in size, is now changing into a static realm where atoms are gradually shrinking. In the past, atoms were larger, which led to the emission of longer wavelengths, allowing researchers to study the fascinating redshift effect. The Big Bang, a concept that Hoyle disliked, is disregarded and turns into a brief moment when all atomic masses are almost zero. This image suggests that cosmic background radiation is not simply a remnant of the Big Bang. Still, it could instead be starlight from a previous era of the universe, scattered and transformed by massive atoms during a time of minimal mass. By adjusting the G knob on the Dream Machine so that the G variation was small enough to match observations, but still significant enough to support GLC2 equals m, Karl Brands and Dicke, who endorsed the scalar tensor theory because it allows G to change with expansion, asserted with confidence that the universe follows Mach's principle. The Brands-Dicke universe has proven to be almost identical to a universe where G stays constant, because if G variation exists, it is tiny, according to theoretical studies of helium synthesis in the early universe and radar observations of orbital motions in the solar system. One of the most intriguing aspects of the scalar tensor theory is the notion that any scalar tensor universe can be transformed into another scalar tensor universe. A Brands-Dicke universe of G variation can become a Hoyle-Nalika universe of M variation, and both can evolve into a universe of C variation. These concepts can readily take on various forms, and they can all return to a regular general relativity universe by either eliminating. Howard Robertson stated in 1933, "We think the main theory is a significant component of general relativity as we examine various cosmologies." These words, from relativistic cosmology, represent the opinions of the majority of cosmologists who would also concur with Denis Sciama. A rigid theory has not yet been discovered. While the choice of a specific model may currently depend on personal preference, we hope that in the future, more evidence will help us test its accuracy and find a satisfying answer. As we shall see, for example, general relativity, the best theory of space, time, and gravity to date, is consistent with an infinite number of different possibilities, or models, for the universe's history. Since only one of these models can be true, the theory permits possibilities that nature does not acknowledge. To put it another way, the theory covers too much ground. We have another way of putting this. Anything can happen if there is no theory. Even with a weak theory, too much can happen. As of yet, no sufficiently robust theory has been found. A model offers a third possibility. It may be accurate, but still not applicable. A theory can only be right or wrong. Even though Einstein rejected this blunder, cosmologists continue to use the cosmological constant, represented by the Greek letter A, repeatedly. George Gamow, My World Line, 1970. The cosmological constant is also referred to as the cosmological term and the cosmical constant. Much later, during a conversation about cosmological issues with Einstein, he candidly shared that adding the cosmological term was the greatest mistake he ever made in his life. William McCrea emphasized Lemaître's revolutionary theories in an interesting 1970 paper called Cosmology Today, arguing that Lemaître was probably the first to relate the fascinating problem of galaxy formation to the larger evolution of the universe as investigated by relativistic cosmology. Lemaître suggested that the time spent close to the Einstein state in his model was essential for the formation of galaxies and clusters of gas clouds, and that during this phase, a delicate balance be true. For now, I will treat A as an unknown element to demonstrate its impact on the models, while also keeping the door open for the possibility that this term could be more suitably integrated into a future, more comprehensive theory. We can speculatively conclude that we should think about eliminating the cosmical terms that include the cosmical constant if we consider general relativity to be a standalone theory. However, retaining those cosmical terms could offer significant flexibility in integrating with other facets of a physical theory if general relativity is only one component required to construct a thorough theoretical model of physical reality. Imagine a wide variety of universes, some of which are constantly evolving while others are in a steady state, all of which are teeming with intelligent beings. What are the chances of living in a universe that is constantly changing? Since every steady-state universe is infinitely long, meaning it can support an infinite number of intelligent beings. In contrast, an evolving universe can only support life for a finite amount of time. So, if steady-state universes are real, the likelihood of living in one is certain. In contrast, the possibility of existing in an evolving universe is non-existent. However, our universe is anything but static, which leads us to believe that there are probably no habitable, steady-state universes. The concept of dual timescales, an atomic timescale that utilizes nuclear processes to measure time, and a dynamic timescale that tracks time through the movements of planets and other celestial bodies, is one of Edward Milne's intriguing ideas. Milne, 1896 to 1950, highlighted three key ideas. I, the significance of the cosmological principle, a term he coined. Ing, the difference between the world map and the world picture. And ECSI, the crucial role of operational methods for measuring distances, similar to radar techniques. The stories surrounding theories of knowledge can be fascinating, but if we jump in too soon, we might see the entire tree of knowledge fall apart. Eddington Tilner dug into their investigations and raised interesting questions. It might be fair to say that scientific microscopes can withstand in-depth and critical examination. Fred Hoyle offered an interesting viewpoint in 1948. We can arrive at a stationary universe with expansion properties without the use of a cosmical constant if we integrate the ongoing creation of matter into the field equations of general relativity. The idea is explored in this work, which was inspired by a discussion with Mr. T. Gold, that we could imagine an expanding universe with a constant proper density of matter through continuous matter creation. The perfect cosmological principle is extremely vulnerable, which is why I find it valuable. It can be shot down by experiment and observation much more easily than the usual cosmological principle. You will see that too. The essence of a scientific hypothesis is to take a bold stance and be open to scrutiny and challenge. Therefore, we see how those far-off regions looked ages ago when we look into the far reaches of the universe. It is necessary to assume that the laws of physics are the same in both cases to make a meaningful comparison between these far-off and nearby regions. The ones in the vicinity assume that the laws of physics are the same in both cases. Since the universe affects all physical laws and encompasses everything that we can see, it is reasonable to assume that it transcends all of our senses. Were the laws of physics the same in the past as they are today? Jayant Narlikar, Steady State Defended, 1973. Narlikar echoes the perspective put forth by Bondi and Gold, suggesting that we can only trust the invariance of natural laws in a universe that remains eternally unchanged. However, this argument has a significant oversight, as it presumes that the concept of the universe as a whole is confined to space alone. I is limited to space on its own. This interpretation is constrained. A more comprehensive view acknowledges an immutable universe that transcends the boundaries of space and time. The concept of the unity of the universe, which embodies the laws of nature, is a notion that spans all of space-time, rather than being a spatial entity that changes over time. Exploring the universe. I'm looking for a comprehensive history that aligns perfectly with the universe. The world should not be confined to fit our understanding, as has often been the case. Instead, we should broaden our experiences and open ourselves up to truly embrace the vastness of the world around us. We kick things off with a thought-provoking quote from Arthur Eddington in his book, The Expanding Universe. For the reader resolved to eschew theory and admit only definite observational facts, all astronomical books are banned. There are no strictly observational facts regarding the celestial bodies. Astronomical measurements are, without exception, observations made from a terrestrial observatory or station. It is only through theory that we can transform these observations into an understanding of the universe beyond our own. Without books and theories, our celestial observations remain devoid of depth and meaning. We create fascinating universes that serve as reflections of our reality. Our desire for ultimate truth leads us to think that the universe we experience in our society is the only one that exists. Every society creates its unique universe, interpreting its observations through the lens of that distinct reality. The diverse historic universes, from Babylonian and Egyptian to Platonic, medieval, Newtonian, and Victorian, each offered unique perspectives deeply rooted in the impactful observations of their believers. Without the weight of our assumptions, we take in the world around us, valleys, hills, rivers, and buildings, all set against a vibrant daytime sky illuminated by the sun, and a mysterious nighttime sky graced by the moon, twinkling stars and planets. What in this image holds cosmological importance? As knowledge and technology have evolved over thousands of years, an increasing portion of the visible world and the realms uncovered by advanced instruments has gained cosmological importance. In today's physical universe, even a simple metal coin tells an incredible story about the stars that perished long before our solar system came into being. So it's fascinating to realize that the universe is not just ancient, but stretches across billions of light years and is home to countless galaxies. Cosmography reveals the essential truths about the universe. This offers a concise overview, divided into 3 engaging sections: local phenomena observations, intermediate distance phenomena insights, and cosmic distance phenomena explorations. When we talk about local observations that hold cosmological significance, we focus on the solar system, our galaxy, and the local group. These fascinating insights stretch out only a few million light-years at most. They assisted us in setting up the following: the initial stages in a distance ladder, the spread and concentration of matter, the ages of stars and the galaxy, which helps us define the boundaries of the universe's age, the rich variety of elements, especially the light ones like hydrogen, deuterium, helium, and lithium, are influenced by the conditions present in the early universe, the cosmic background radiation, CBR, that comes from this early universe and uncovers the unique motion of our galaxy, the parameters of the cosmos. Local conditions provide insights into the age of the universe T0, the current baryonic density PB0, and the value of the combination D0H2, which involves the density parameter and the Hubble term. When we dive into intermediate distance observations, we're looking beyond the local group of galaxies. These observations primarily spotlight the local, or Virgo, supercluster and stretch out to a few hundred million light-years away. These observations concentrate exclusively on the sub-Hubble sphere and do not reach into the complete Hubble flow. Still, they play a crucial role in setting up the fascinating structure, captivating distribution, and dynamic motion of galaxies. The broader range of distance scales, the redshift distance and redshift velocity connections. The cosmic parameters. These fascinating observations reveal the age and baryon density of the universe, along with the values of the Hubble term H0 and the density parameter D0. Remote insights. Incredible observations reach out many billions of light-years beyond the local supercluster, pushing the boundaries of what we can see in the observable universe. These fascinating deep space observations, each carrying immense cosmological importance, reach well beyond the sub-Hubble sphere and contribute to establishing cosmic distances. The redshift distance relation takes on a non-linear form, and the linear velocity distance law necessitates that what we observe in the world picture is mapped onto the world map. Fascinating evolutionary histories that enable us to draw intriguing comparisons between nearby and distant astronomical systems. The cosmic parameters. In summary, it's clear that we still have quite a journey ahead to achieve a precise and secure understanding of the values for the Hubble term H0, density parameters dB0 and D0, deceleration term Q0, cosmological term A, and the curvature constant K. To uncover the rate at which the universe is expanding, known as the Hubble term H0, along with its deceleration, and the global geometry characterized by the curvature constant K, we need to explore the distances and redshifts of distant and faint systems. Determining distances can be quite challenging, but the good news is that measuring redshifts is a much simpler task. We begin by exploring nearby astronomical systems within the sub-Hubble sphere, where peculiar motions take precedence over the Hubble flow. Gradually, we build overlapping distance indicators that extend beyond the sub-Hubble sphere into the fully developed Hubble flow, allowing us to apply Hubble's linear redshift distance law. Imagine a staircase, each step drawing us deeper into the vastness of space. As we move forward, it's essential to recognize that with every step we take, approximations build up and uncertainty increases. Let's kick things off with the astronomical unit, which is the distance from the Earth to the Sun, and the year representing the Earth's orbital period around the Sun. A body located 1 parsec away, equivalent to 3.26 light-years, creates an angle of 1 arcsecond when viewed from 2 points that are 1 astronomical unit apart, positioned along a line that is perpendicular to Hubble's law. This fascinating concept ties together clustering galaxies, supernovae and globular clusters, including Cepheid variable stars and RR Lyrae variable stars, all of which are essential for main sequence fitting and parallax measurements. The apparent magnitude, represented as m, gauges how bright a source looks to us, typically within a particular spectral range, while the absolute magnitude, noted as m, indicates how bright that source would shine if it was situated 10 parsecs away. Once we determine the absolute magnitude m of a source, we can uncover its distance L. The movements dictate the absolute magnitude, taking precedence over the Hubble flow, and are presented at a distance of 100 million light-years for illustrative purposes. The light year, a fascinating concept in cosmology, represents the distance that light travels in one complete year of the Earth's orbit around the Sun. It's a more straightforward way to grasp the vastness of space. Parallax measurements extend our reach beyond the solar system, allowing us to explore distances of 100 light-years, 0.03 arc-seconds, and, with increasing uncertainty, even up to 300 light-years. Recent statistical parallax measurements, averaged over numerous stars in an open cluster, along with data from satellites positioned above the Earth's atmosphere, have successfully extended the range to an impressive 1,000 light-years, 0.03 arc-seconds. The Hyades, a fascinating group of stars located just 46 parsecs, 150 light-years away, stands out as the closest and most significant open cluster in our galaxy. A variety of exciting methods for measuring distance, all calibrated by the renowned Hyades standard distance, are now stepping into the spotlight. The moving cluster method encompasses the Hyades and various other open clusters located at greater distances. The essential main sequence fitting method measures the distances of star clusters, such as the Pleiades, about the Hyades, extending our distance measurements to the far reaches of the galaxy. Addressing the issue of extinction, or interstellar absorption, of starlight presents a significant challenge. The fascinating concepts of apparent brightness and the inverse square law are crucial when it comes to tackling the astronomical challenge of measuring distances. Our observations reveal that the evidence points to the Sun's absolute magnitude, with a luminosity of L8 being 4.7. We use L to signify luminosity, setting it apart from L, which stands for distance. A Sun-like star in the M5 cluster, located 1 megaparsec away, shines with an apparent magnitude of M30. This brightness is far beyond what ordinary ground-based telescopes can detect, and is only just within the capabilities of the Hubble Space Telescope. Bright RR Lyrae stars and pulsating Cepheids, with their fascinating connection between brightness and pulsation periods, play a crucial role in measuring distances to the far reaches of the galaxy, globular clusters, the Magellanic Clouds, and other nearby galaxies. By applying various corrections for factors that influence apparent magnitude, including differing heavy element compositions and extinction within our galaxy and beyond, these stars broaden our exploration to the edges of the local group. The typical density of astronomical systems tends to drop as their size grows larger. The density of matter in the disk of the galaxy close to the Sun is approximately 1 solar mass per cubic parsec, which translates to about 10 hydrogen atoms per cubic centimeter, with interstellar gas making up roughly 10% of that total. Did you know that the total mass of our galaxy within the Sun's orbit is around 200 billion solar masses? That's right. And interestingly, about half of that is made up of luminous matter, which we see as stars. Fascinating. The total amount of glowing matter in the galaxy beyond the Sun's orbit is considerably less, suggesting that the overall luminous mass of the galaxy is probably not much more than 100 billion solar masses. Many spiral galaxies exhibit comparable, constant rotation velocities as well. The fact that rotation velocity remains constant over such vast distances suggests that a significant portion of our galaxy's mass is located beyond the Sun's orbit, likely in the halo, with the total mass potentially reaching up to 10 to the power of 12 solar masses. Did you know that a staggering 90% of the matter in the universe, which plays a crucial role in keeping large astronomical systems bound together, is non-luminous? It's a fascinating aspect of our cosmos that often goes unnoticed. Dark matter is a real thing. What it is, though, remains a mystery. Some intriguing possibilities for dark matter include vast molecular clouds floating in interstellar space. These brown dwarfs are too small to start hydrogen burning like Jupiter. These low-luminosity red dwarfs can manage to burn hydrogen, white dwarfs, remnants of supernovae like neutron stars and black holes, and even more elusive forms of matter such as primordial black holes. There could be vast, yet-to-be-discovered populations of brown dwarfs, red dwarfs, and black holes, known as machos, massive compact halo objects that might hold the key to solving the dark matter mystery. Gravitational lensing, which involves the bending of light from distant objects by those in the foreground, presents an exciting opportunity to uncover dark matter in our galaxy, mainly if it exists in compact forms. The mass-to-light ratio serves as an essential tool in exploring the mysteries of dark matter. The universe predates the galaxy by 1 or 2 billion years, while the galaxy itself is younger than the oldest stars by under 1 billion years. By dating the birth of the oldest stars, we can establish an approximate lower limit on the age of the universe. Stars shine brightly for a limited time on the main sequence, thanks to their finite supply of hydrogen. As their mass decreases, their luminosity diminishes, leading to an extended luminous lifetime. The mystery surrounding the origin and age of chemical elements has largely been unraveled. Up until the early 1900s, astronomers believed that the Sun's makeup was quite similar to that of our planet, Earth. We've discovered that the Sun and other main sequence stars are mostly made up of hydrogen and helium, with just tiny amounts of other elements sprinkled in. In the late 1940s, George Gamow proposed that elements heavier than hydrogen were formed during the universe's early stages. Recent studies reveal that in the early universe, just 200 seconds after its birth, only the light chemical elements, deuterium, helium, and lithium, were formed through this process. Every star on the main sequence, gradually transforming hydrogen into helium, has contributed around 1 to 2% to the original helium abundance. The synthesis of heavy chemical elements, such as carbon, oxygen, iron, nickel, thorium, and uranium, occurred in stars, and their current abundances offer fascinating insights into the history of our galaxy. The wealth of light elements provides fascinating insights into the history of the early universe. In 1964, Fred Hoyle and Roger Taylor at Cambridge University tackled the intriguing challenge of explaining the significant abundance of helium. The helium fraction of matter by mass is around Y0.25. They demonstrated that a hot Big Bang could effectively address the problem. Check where you'll find the anticipated amounts of light elements showcased according to the latest calculations, aligning with the current average density of baryonic matter. Baryonic matter is all about those fascinating atoms that are built from protons and neutrons. The calculations take into account a background radiation temperature of 2.73 Kelvin and consider only 3 types of leptons: electrons, muons, and tauons. The amount of deuterium is exceptionally responsive to the density of baryonic matter. A portion of interstellar matter goes through an exciting cycle via stars, including star formation, stellar winds, novas, and supernovas, while some of the ancient deuterium is transformed into helium. As a result, the early universe generated a greater amount of deuterium than what we see today. Figuring out the original deuterium abundance becomes easier when we look at the combined abundance of 3 He-D, since deuterium transforms into helium-3. The observed levels of dark matter is out there, but what about the missing matter? Does it exist? If the universe experienced a phase of inflation in its early days, an idea that has gained traction lately, then it's highly probable that the density parameter d0 is valued at 1. In this scenario, there's a notable divide between PB0 and P0, suggesting that the missing matter is the key player in the universe. Cosmic background radiation is a fascinating topic that captures the imagination and curiosity of many. It's a remnant from the early universe, offering insights into the origins of everything we know. Exploring this phenomenon can lead to engaging discussions and a deeper understanding of our cosmos. Since 1941, astronomers have discovered that specific molecules in interstellar space respond to low-energy radiation in fascinating ways. Eventually, radio astronomers stumbled upon a consistent noise or hiss in their receivers that initially seemed to lack any clear explanation. The insights into molecular excitations and radio noise have finally come to light. Arno Penzias and Robert Wilson from Bell Telephone Laboratories meticulously removed every conceivable source of interference from their radio receiver and horn-shaped antenna in Holmdel, New Jersey. At last, they reached an ultimate noise level at a temperature of about 3 Kelvin. The intriguing sound appeared to come from beyond our world. At the same time, James Peebles, a young astrophysicist at Princeton University, was revisiting the calculations that Ralph Alpha and Robert Herman had made about a decade earlier. They were diving into the fascinating concept of a scorching early universe and the remnants of cosmic background radiation we see today. Penzias and Wilson took notice of this work. Back in 1965, a groundbreaking discovery was made by Robert Dick Peebles and their team at Princeton University. They identified the radio noise that Penzias and Wilson had detected as the cosmic background radiation, a pivotal moment in our understanding of the universe. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their remarkable and unexpected discovery. The cosmic background radiation, CBR, which is separated from matter at a redshift of 1000, currently boasts a temperature of 2.728 Kelvin, as measured by advanced infrared detectors. The Cosmic Background Explorer, COBE satellite, has revealed 2 unexpected findings that are sure to intrigue listeners. Initially, the intensity closely aligns with the blackbody curve of thermal radiation, deviating by just 1 part in 10,000. Next, once we eliminate the notable 24-hour fluctuations, where the peaks and troughs are in contrasting directions in the sky, the radiation reveals an unexpectedly consistent pattern showing only minor variations. Based on the significant 24-hour anisotropy, it's clear that our galaxy is cruising at an impressive speed of 600 kilometers per second, heading straight for the constellation Leo. The tiny anisotropies, usually just a few parts in 10 to the power of 5, are remnants from the time of decoupling, around redshift 1000. These subtle variations are the fingerprints of density irregularities in matter that eventually transform into galaxies, clusters of galaxies, and superclusters. Cosmological parameters are fascinating topics that can engage listeners. We uncover so much about the universe, not just by venturing into the distant reaches of space, but by diving into the rich layers of our history. The oldest stars suggest that the universe is at least 16 billion years old, which raises intriguing questions for the Friedmann universes, unless the Hubble coefficient H is below approximately 0.6. Based on the wealth of light elements produced in the early universe, we can deduce that the average baryonic density is roughly 10 times greater than that of luminous matter. In an Einstein de Sitter universe, where D remains consistently at 1 and is composed solely of baryonic matter, the Hubble coefficient HR0 is measured at 0.14. This figure is generally considered too low by the majority of astronomers. Higher values of H call for non-baryonic additions known as missing matter. The term missing highlights that non-baryonic matter, if it exists, is not just dark like most baryonic matter, but is also currently a mystery. The cosmic background radiation is a fascinating phenomenon that serves as our most substantial evidence of the universe's uniformity. Its nearly uniform nature and consistent temperature, along with slight variations, reveal the early stages of galaxy formation. This captivating topic opens up a world of exploration into the origins of our cosmos, exploring the fascinating structure, distribution, and motion of galaxies. Exploring galaxies, from their unique compositions and structures to their fascinating motions and emissions, offers us valuable insights that help us better understand more distant galaxies. We explore the fascinating world of galaxies, both near and far, to uncover how they can serve as incredible markers of distance, all while considering the impact of evolution. The local group, featuring two massive spiral galaxies, our galaxy and M31, is an exciting collection of galaxies, predominantly consisting of dwarf systems that typically move at speeds ranging from 100 to 200 kilometers per second. Beyond the local group, there are a multitude of nearby groups that showcase a fascinating variety of galaxy types, including ellipticals like M87, spirals such as M81 and M101, irregulars like M82, and an array of dwarf galaxies. These groups extend out to the fascinating and diverse Virgo cluster, which boasts thousands of galaxies located 70 million light-years away. The incredible array of clusters creates what we call the local supercluster, or the Virgo supercluster, a fascinating topic to dive into. It includes over 1 million galaxies, packed into a cube, measuring 200 million light-years on each side. The Coma and Perseus clusters are impressive gatherings of galaxies, much like the well-known Virgo system. In the 1950s, Gérard de Vaucouleurs introduced the concept of a local supercluster of galaxies, which he named the supergalaxy. This concept emerged after Vera Rubin's groundbreaking research on the systematic, peculiar flow, velocities of galaxies. Surveys of galaxies beyond our own have validated his idea and revealed that the universe is made up of numerous superclusters, connected by luminous regions and divided by vast, dark voids. Superclusters create massive blocks or plates, much like the tectonic plates that shape the Earth's surface. As the cosmic blocks stretch out, their gravity keeps them somewhat bound, leading to a slow but steady widening of the gaps between them. Every block features significant internal systematic movements, which complicate the quest to determine the actual value of the Hubble term. In the fascinating world of astronomy, we frequently determine how far away a source is by analyzing the luminous flux we receive in comparison to what it emitted initially, as illustrated in equations 19.1 and 19.2. This approach does come with the caveat that the emitted flux needs to be understood. To determine the distance to the source, it should be comparable to closer sources with known luminosity. As we embark on our exciting journey beyond the galaxy, we utilize stars and star clusters as our trusty guides for measuring distances, drawing comparisons with closer stars and star clusters, whose distances are already established. Bright RR Lyrae variable stars can be observed up to a distance of 1 million light-years, while the pulsating Cepheid stars extend that reach to 10 million light-years. Globular clusters, which have known sizes and absolute magnitudes, can be seen up to 30 million light-years away, and supernovas of type Ia, with their known luminosity, can be detected at least 100 million light-years from us. In the intermediate universe, we explore vast distances stretching across several hundred million light-years, allowing us to peer back in time by several hundred million years. The evolutionary changes in stars, globular clusters, and galaxies over one galactic year, around 200 million years, tend to be subtle, and identifying dependable standard candles isn't the most significant challenge we face. The distances we measure in the cosmic landscape, whether through the lens of backward light or on the world map where the velocity-distance law applies, show remarkable consistency. The mass m and radius r of a gravitationally bound system are connected through an intriguing concept called the virial theorem. We need to figure out how the spiral galaxy is angled about our view. Every approach to gauging distances beyond our galaxy comes with its own set of challenges and uncertainties, making the entire topic feel more like an art form than a strict scientific discipline. So many questions to explore. Consider this intriguing question. Why is it that our galaxy hasn't witnessed a supernova since 1604, while other comparable galaxies experience one approximately every 50 years? It's a fascinating mystery that begs for exploration. The local universe, encompassing nearby distances, is where the fascinating movements of stars and galaxies take center stage, overshadowing the broader trend of everything drifting apart due to the universe's expansion. We notice distinct internal velocities derived from the Doppler-shifted emissions and absorptions across various sections of the system, or just from the Doppler-broadened lines of the entire system. The total mass m encompasses all forms of gravitational matter. The velocity u can represent a rotational velocity in a spiral galaxy, the relative velocity of two galaxies orbiting one another, or the typical velocity of numerous galaxies within a cluster. In all these scenarios, m signifies the mass of the system. Measuring mass in this manner reveals that the mass-to-light ratio m equals 1 often rises with the system's size, leading to a greater proportion of dark matter. Let's choose spiral galaxies with comparable ML ratios. The Doppler-broadened spectral lines of 21 centimeter radiation, influenced by disk rotation, are directly linked to their mass m, as outlined by the virial theorem. The mass m is directly related to luminosity L through the well-established m equals L ratio. Therefore, a connection can be observed between line width and luminosity, or absolute magnitude. The Tully-Fisher relation, introduced by Brent Tully and Richard Fisher, enables us to measure distances to spiral galaxies located up to 300 million light-years away by analyzing line widths and apparent magnitudes. It's essential to adjust redshifts and velocities to account for the unique motion of our planet, Earth. This is how Hubble initially figured out h0 and discovered that h was roughly 5. It's important to highlight that when we plot log z or log cz against m, the resulting curve showcases a slope of 0.2. This is because, at intermediate distance scales, we aren't making a distinction between the world picture and the world map. There are a few key points to consider. First, the linear relationship between Hubble's redshift and distance is just an approximation. Second, the Fizeau-Doppler connection between velocity and redshift is also an approximation. And third, we haven't successfully translated the observable universe into a map that reflects the fundamental velocity-distance law. Relying on these rough equations for higher redshifts places us in a tricky position. In the latter part of the 20th century, two competing schools emerged. The first approach, championed by Alan Sandage and Gustav Tolman, suggested that h0 is around 50 kilometers per second per megaparsec, h equal to 0.5. In contrast, the second perspective, introduced by Gérard de Vaucouleurs, proposed that h0 is approximately 100 kilometers per second per megaparsec, h equal to 1. Various distance indicators, correction techniques, and selection effects contribute significantly to the discrepancies in their findings. Since the era of Hubble, cosmologists have continually been amazed by the intricate and vast nature of cosmic inhomogeneity. The sub-Hubble sphere, the exciting domain of intermediate distances, has been growing in size thanks to remarkable advancements in observational techniques. Incredible luminous arcs are now sweeping across vast areas of the extragalactic sky, serving as an enticing hint of the concealed realms of dark matter. We've reached an exciting point in cosmology, where the sub-Hubble sphere exhibits systematic streaming motions, with velocities that reach and even exceed 10,000 kilometers per second. Astronomers hold a unique edge over geologists because they can witness the past unfold directly before their eyes. The universe is constantly changing, and the distant objects we observe need to be connected to our understanding of the world. This is the only way to piece them together into a cohesive and meaningful picture. The most straightforward mapping process uses just the deceleration term. Things change over time, and when we look back from a far-off perspective, they appear quite different from what we see around us today. The evolution of the universe adds layers of complexity to our understanding of cosmological development. Just as we explore how the fundamental concept of distance affects our daily experiences, this is the type of distance we should highlight on the world map. The world map features a beautifully curved space that captivates the imagination. The Robertson-Walker metric provides a comprehensive framework for understanding geometric or tape-measured distances in the velocity-distance law. Another fascinating operational distance is known as the apparent size distance, LDA. In a flat static space, a source with a diameter of d, positioned at a distance of L, creates an angle of 6.0 d equals L in radians. Sadly, with this approach, many galaxies and galaxy clusters that are far away seem smaller than their actual size. This intriguing phenomenon occurs as the outer regions of galaxies, which are less luminous than their inner parts, often remain hidden from view. We need to address this and other factors, and the outcomes come with a notable level of uncertainty. Our small redshift relations fall short in surveys that extend well beyond the sub-Hubble sphere, necessitating the use of more precise connections. Specific models, such as the Friedmann models, illustrate these connections, as highlighted in the findings. Our journeys through the universe, both ancient and distant, have yet to arrive at a unified model that everyone agrees on. Impact of evolution. The evolution of galaxies and their clusters over long periods is an incredibly intriguing topic that is just beginning to be explored. Cosmologists are on a mission to identify galaxies with specific luminosity, using them as standard candles to measure distances across the universe. Occasionally, the most dazzling galaxies within abundant clusters that we discover when considering second order in Z are those where Th1 equals H0, representing the Hubble time. When we confine our focus to Z0.1, we find that the maximum permissible look-back time exceeds just over 1 billion years, and the evolutionary changes observed in most galaxies are relatively minor. We need to determine the look-back time for larger redshifts based on specific models. Do galaxies shine brighter or dimmer as they age? While some might think they would diminish, both theory and observation indicate that vibrant galaxies at the heart of rich clusters are consuming smaller galaxies, expanding in size and becoming even more colorful along the way. The transformations happening in galaxies are so significant that they overshadow the slowing down effect. This indicates that the evolution of galaxies takes precedence over the evolution of the universe itself, rendering the traditional approach of using brightness and redshift to determine H0 and Q0 less relevant today. Solid-state detectors are incredibly powerful, boasting sensitivity 100 times greater than traditional photographic plates. They uncover a staggering number of faint galaxies, up to 100 per square arc minute, so far away that their light has been traveling for most of the universe's existence. Quasars shine like dazzling beacons across the vast cosmos, yet their varying levels of brightness render them unreliable for measuring distances. It's widely believed that most quasars and other active galactic nuclei emerge during the formative phases of galactic evolution. The impressive redshifts of numerous quasars, like PC 124734006 at Z 4.89, reveal that galaxies were already in existence when the universe was likely only about 10% of its current age. Quasars were incredibly abundant in the past, especially at redshifts between 3 and 4, but their numbers have significantly decreased since then. Absorption lines at various redshifts in their spectra indicate the potential existence of vast clouds of intergalactic gas that have yet to condense into galaxies. What's the journey of galaxy clusters like as they evolve? The X-ray emission from intergalactic gas in rich clusters has seen a rise over time, and this finding backs the idea that large clusters are likely younger than galaxies. The magnitude-redshift relation, equation 19.29, along with various modifications and different selection procedures employed by astronomers, has been a fundamental tool in modern observational cosmology since Edwin Hubble's era. The goal has been to assess through observations the value of H0 at lower redshifts and the value of Q0 at higher redshifts. Nonetheless, observations can be quite perplexing at smaller redshifts because of significant sub-Hubble systematic motions, and at larger redshifts, they are influenced by evolutionary effects. The idea of applying inexact relations beyond their intended scope hangs over the whole topic. For instance, the linear redshift distance relation established by Hubble starts to falter at moderate redshifts, necessitating the development of a more accurate relation within the framework of a specific model. To wrap things up, we still have quite a journey ahead before we can confidently pin down the values of the Hubble term H0, the density parameters dB0 and D0, the deceleration term Q0, the cosmological term A, and the curvature constant K. Since 1900, cosmologists have been on a quest to uncover the answer to this intriguing question, sparked by Carl Schwarzschild's pioneering effort to measure the curvature of space. It's interesting to observe that none of the approximate expressions resulting from the expansion of the Hubble term in the equation include the curvature constant K. At low redshifts to the second order, the geometric distance L, as defined by the Robertson-Walker metric, remains unaffected by curvature. What we see in far-off areas reveals the speed at which the universe is expanding, the Hubble term H0, and how it slows down, the deceleration term Q0. Yet it doesn't provide insight into the curvature of space. We can uncover the answer to our question solely within the framework of specific models or families of models, like the Friedmann models, by examining the values of H0 and Q0. There's still no agreement on what the right model is, and it feels like we're just as far from a solution as we were back in Schwarzschild's time. The discussions surrounding the universe's openness or closeness are still very much alive. Most cosmologists operate under the assumption that general relativity holds on a cosmic scale, even though this has yet to be definitively proven. Additionally, a significant number of them are convinced that the A-force is non-existent. The universe follows the Friedmann model. Based on these assumptions, we can explore three exciting methods to figure out whether a Friedmann universe is open or closed. To start, we examine the age of the oldest stars and compare it to the critical age, T Crete. Next, we discuss the observed density of the universe and compare it to the necessary density, PCIT. Finally, we take a close look at the observed value of Q0 and measure it against the required value of 0.5. When we focus on this specific group of models, the overwhelming evidence suggests that our universe is open, which means it extends infinitely in space. If the A-force is indeed present, then this conclusion may not hold. Imagine if redshifts are actually shifts in velocity, and that the nebulae are moving away from us. The law of redshifts reveals insights not just about the space between nebulae, but also about the intriguing short value of T, 1.8 billion years, that has been confidently reported. In this context, T represents the inverse of the Hubble term. A candle flame viewed from a distance of 1 kilometer shines with a brightness comparable to that of the first magnitude stars, Aldebaran and Altair. Polaris, the pole star, shines at a second magnitude, M2, resembling a candle flame from afar. 2.5 and 1.6 kilometers. The greater the magnitude, the dimmer the visible brightness of the source. A candle flame viewed from 10 kilometers away appears 100 times fainter, making it comparable to a sixth magnitude star, M6. Sources that shine brighter than 0 magnitudes have negative magnitudes. For instance, Sirius at M1.6, Venus at M4, and the full moon at M12.5 are, respectively, 10, 100, and an astonishing 250,000 times brighter than a star of first magnitude. According to the rule, brightness relates to 2 to 5 times the inverse of the distance, while the inverse square rule indicates that brightness is connected to 1 equals L squared, with L representing the distance from the source. L2 is found to be proportional to 2.5 times m-1. However, 25500 indicates that L is proportional to 10 to the power of -1 equals 5. Astronomers characterize the absolute magnitude m as equivalent to that of a first. The brightest star, located 10 parsecs away, has an absolute magnitude of m. So, the universe is continuously expanding in its entirety. There's no inherent requirement for a linear expansion law or a strict proportional relationship between redshifts and distance. The general theory suggests that the law should move away from a linear approach. When we have a large enough sample, we can identify the departure and determine its trend. This information would instantly narrow our reality to a defined selection of potential worlds. The flux F from a source and the number n of sources leading to the observed source are, in principle, quantities we can observe, and the findings remain unaffected by redshift measurements. If the observed flux changes at a rate that is either faster or slower than the number n raised to the inverse 2/3 power, it suggests that the sources may not share similar luminosities, or that the sources are evolving, or that space is not static, or that the geometry of the universe deviates from being Euclidean. Astronomers had high hopes that the 2/3 rule would serve as an easy way to test the universe's geometry. However, in reality, the challenges of choosing comparable sources and the impacts of evolution render the determination of space curvature through this method quite impractical. In the 1950s, radio astronomers such as Martin Ryle and his team made groundbreaking discoveries, providing the first solid evidence that the universe is constantly evolving. Back then, only a handful of radio sources had their redshifts identified through their optical counterparts. Instead, radio astronomers relied on number counts. Researchers discovered that the quantity of faint and likely very distant radio sources per unit volume significantly surpassed that of bright and presumably closer radio sources. This compelling evidence highlights the substantially greater abundance of radio sources in the past compared to today, effectively challenging the fundamental principle of the steady-state theory. Optical astronomers have uncovered an exciting finding: a greater abundance of quasars in the past. This discovery adds compelling evidence to the idea that our universe is constantly evolving. Did you know that our closest bright quasar, 3C273, is a staggering 500 megaparsecs away? It's fascinating to think about the vast distances in the universe. During the period corresponding to a redshift of Z 2 to 2.5, the closest quasar would have been a staggering 30 times nearer and shining as brightly as it did in that ancient time, long before the Earth came into existence. In Discovery of the Cosmic Microwave Background, 1990, Robert Wilson shares, "Arno and I, of course, were thrilled to have any answer to our dilemma finally. A solid explanation likely brought us some joy. Initially, neither of us embraced cosmology with much seriousness. We had become familiar with the idea of steady-state cosmology. I, coming from Caltech, had witnessed many visits from Fred Hoyle. The steady-state cosmology is quite intriguing from a philosophical perspective. So, let's share our findings clearly and engagingly. This measurement remains relevant, even if the cosmological model isn't entirely accurate anymore. In the first 3 minutes, 1977, Steven Weinberg states, "The detection of the cosmic microwave radiation background in 1965 was one of the most significant scientific discoveries of the 20th century. What a twist that it happened by chance. Alternatively, what prevented a thorough investigation into the radiation before 1965? The technology was there, yet no one had thought to dive into an exhaustive search." Weinberg shares 3 compelling reasons. Initially, the triumph of stellar nucleosynthesis appeared to remove any necessity for primordial nucleosynthesis, lending support to the steady-state theory. Secondly, there was a breakdown in communication between theorists and experimenters. Theorists were unaware that 3 Kelvin radiation could be detected, while experimenters like Penzias and Wilson did not recognize its potential existence. Before 1965, many physicists found it challenging to take cosmology seriously, often viewing anything about the early universe as mere fanciful speculation. Gérard de Vaucouleurs, alongside Alan Sandage and Gustav Tammann, produced estimates of the universe's size based on the Hubble constant that varied significantly, differing by a factor of 2. Additionally, when I inquired with the main characters about the boundaries beyond which they couldn't envision the Hubble consistently being untruthful, these boundaries didn't even intersect. The concept of dark matter in the universe has been around for quite some time. Back in 1907, Edward Fournier d'Albe, in his work Two New Worlds, highlighted a fascinating idea. The mystery of the night sky's darkness could be unraveled by considering that for every bright star, there might be a staggering 1 trillion dark stars lurking in the cosmos. Astronomers discovered that the amount of dark matter was significantly excessive for various reasons. In 1922, the Dutch astronomer Johannes Kapteyn, through his studies of the movements of stars near the Sun, confidently stated, we have the means of estimating the mass of dark matter in the universe. That same year, James Jeans added to the conversation with his intriguing observation: there must be about 3 dark stars in the universe to every bright star. Ideally, the question of whether the universe is open or closed is a fascinating Riemannian problem from the 19th century. It deserves to be explored through geometrical surveying, relying solely on the Robertson-Walker metric, without getting caught up in the complexities of 20th century Einsteinian dynamics. The nonlinearity of the redshift distance relation takes center stage here. The initial segment of the redshift distance relation is crucial for determining the Hubble constant. Moving forward, the subsequent and more intricate terms assist us in uncovering the deceleration constant, while even more elaborate terms lead us to the curvature constant. Right now, we're diving into the exciting early phases of this cosmological project, where we're hashing out the correct value of the Hubble constant. The incredible effects of astronomical evolution have nearly made it impossible to measure the deceleration constant right now directly. Sometimes it's important to remember that in the realm of cosmology, nearly everything is open to interpretation. Have you ever wondered how an astronomer gazing at the night sky can perform specific calculations on paper or a computer and predict with incredible accuracy what another astronomer will observe 1,000 years from now? It's a fascinating concept that highlights the power of scientific methods and the vastness of time in our universe. If you're looking for an answer, I've got you covered. We're totally in the dark here. In 1963, Peter Schur, a radio astronomer from Cambridge, England, famously stated, "There are only 2.5 facts in cosmology. The first fact is that the night sky is dark. The second is, the galaxies are receding. And the half-truth is that the universe's contents are evolving." Are there any additional facts we can include? During a press conference on April 24, 1992, George Smoot unveiled the latest findings from NASA's Cosmic Background Explorer, COBE, satellite, making a striking statement about cosmic background radiation. If you're religious, it's like seeing God. This captivating remark captured headlines across the globe, with newspapers proclaiming phrases like the theory of creation and grand unification of religion and science.